So this week's tutorial will be looking at your assignment and going over the concepts. So if there are any issues you're facing with any of the analysis or something's not making sense, please let me know now so that I can focus on that in this tutorial session. So this tutorial session is purely dedicated to helping you guys with the assignments. There's a lot of things that we can discuss. So I want to go over all of it. So I'll rely on you guys letting me know which bits you are confused with or stuck with so I can focus most of my energies there. Okay, so just let me know in the chat and I'll focus on those bits. So before I start talking about the actual assignment question, just talk a little bit about the theory behind it. So this assignment requires us to design a component, namely a flange coupling, and size its dimensions according to its physical ability to withstand the forces that it will face when it's working. And this is how design engineers, they work, okay? They come up with the conceptual design, something similar to how you're doing your project. You come up with the conceptual design and what you feel would work best. And then you do the actual mathematics, physics, applying engineering theory to then get the proper dimensions so that it will function. All right. And that is the whole idea behind this assignment, sort of giving you a taste as to what is to come. So if you're mechanical or civil, this is pretty much where it all begins for you. You start doing your analysis, and this is the first assignment that you're given, where you start applying some engineering theory. So before any of the analysis you can do, you first have to identify what type of forces you're facing. The whole project is designing it so that it's able to withstand the forces, but there are different types of forces and we have to identify those different types. So can anybody tell me what are some of the types of forces you'll be facing in this assignment? Yes, very good. Shear, tensile, and compressive forces, as well as friction forces. Very good. Frictional forces, they come into play when we have parts that are moving against each other or they are sliding on top of each other. Say our coupling was sliding along the shaft, we would look at the frictional forces as well. But for this assignment, we don't have to worry about frictional forces because we're assuming it's going to be mounted and there won't be any movement between the two parts. So shear, tensile, and compressive, those are the forces. Torque is a product of the force. So torque comes about when we have a force acting at a distance, but torque is not a force. Torque is the reason why we have the force, but is the actual forces that we use to calculate the stresses, and then those stresses we use to calculate whether or not our part will be able to withstand the forces. So it's all to do with forces, basically. We have to convert torque to force, and then we use the force to then calculate the stress. So we have three main types: shear, tensile, and compressive. Tensile and compressive forces are normal, meaning they act perpendicular to the stressed surface, and shear acts parallel to the stressed surface. So if we were to look at a specimen, tensile would be acting away from the surface, perpendicular and away, 90 degrees. Compressive would be opposite, into the surface. And shear is acting parallel to the surface. And this is the stressed surface. All right. So answer the first question. Great. Now, the next question we have to ask ourselves is, when do we know our design is good enough? When do we know that our design will be able to function properly and not fail or not break? How do we know this? Guys, have any ideas? How do we tell when we have designed something properly or adequately? If it's safe for use, yes. So generally we ask ourselves two questions. Is it safe and is it cost effective? All right. Safety and cost are the two things that we mostly look at. That's why for most of your projects, I've suggested that you include either its safety or its cost into your design criteria, because those are two main things that we are always interested in. All right, we are always trying to make sure that number one, our product is safe, and that's safety for the consumer, for the public, for the customer, whatever it is, it's their safety that's paramount. And the second one is the cost. We want to make sure that the cost of it, for us manufacturing it, is low, or the cost for the consumer is low, or the cost that it will incur on our investors or our stakeholders is low. All right, so we always try and find a nice balance between the two. Now, I hope you're all familiar with this curve, the graph, stress versus strain. Have you seen this before? Right, so it's been discussed a lot in your lectures. And for mechanical and civil, it is almost the fundamentals of what we use, okay? Understanding and reading this graph and this curve to be able to understand material properties. So the curve is broken down into two different regions. We have region 1 and region 2. Region 1 is the elastic region. Region 2 is the plastic region. Now, taking for example our specimen, say we load it with some force, with some tensile force. It'll begin to experience some kind of stress. It'll begin to experience tensile stress. Initially down here, it has no load. And as we increase that force, the stress will increase. And at the same rate, the strain will increase. Unique thing about the elastic region is that in this region, the material has a directly proportional relationship between its stress and strain. So as the stress increases, our strain also increases. And the rate at which it increases is called the Young's modulus. That's the relationship between the two. We don't have to worry too much about this right now, but just be aware that that is called the Young's modulus, the gradient of the slope. Now there is a point where the stress and strain no longer have a directly proportional relationship, and the relationship becomes a lot more difficult to try and map. And this mapping is done through experimentation. So is all of these material properties are determined through years and years of experimentation. So there is a certain point where this is no longer a directly proportional relationship. And this point is called the yield stress. And when the material has a yield stress, once it experiences a yield stress and the stress further increases, we further increase the load, our material begins to experience plastic deformation. Now in the elastic region, as soon as we release the force, our shape, our part will go back to its original shape. And that's fine. That's what we want to keep, or that's what we want to see. We never want to try and plastically deform our parts or plastically deform our materials. As soon as we go into the plastic deformation range, that is considered a failure, because no one ever designs a part for it to be able to change its shape throughout its working life. We always want to try and maintain its shape. As soon as it goes into the plastic deformation range or the permanently deformed range, it is no longer effective and we have to replace the part. So that limit is called the yield stress. And we design most of our components to that yield stress. So our working stress, or the stresses that we are going to try and determine when the part is in its use, should always try and be less than the yield stress. And that is how we know if we have designed something adequately. If the stresses induced by its function are less than the yield stress of the material. Now, can anybody tell me what is a factor of safety? Yes, well, while that is true, factor of safety is yield stress over working stress. The factor of safety is the direct relationship between yield stress and working stress. It's the ratio of the yield stress and working stress. Like I was saying, we always try and design our components to be less than the yield stress. But let's say we have a factor of safety of 1, right? That would mean that our yield stress is equal to our working stress. Now, do you think this is a good principle to design your components to, making your yield stress equal to your working stress? No, it's never a good idea. Why? Because it gives you no room or margin for error. If your part experiences some kind of anomaly, some kind of force that wasn't expected, say in the case of our assignment, our shaft suddenly has a power surge and it starts to produce more power than it needs to or than it should, and we experience more torque and as a result more forces, our part will fail. So that's why we always try and keep our factor of safety greater than 1. So long as you have a factor of safety greater than 1, you have some kind of margin for error. One of my lecturers once said that we always work within 10%, you know, engineering is a 10% sort of field where we make all these calculations, but we're within 10% of the actual answer. Science is very specific. Engineering is more, we get within the ballpark, but we don't get the exact numbers. So we always try and have a margin for error. So what will be the limit for FOS? Okay, so like I was saying, a factor of safety can be anything. Sometimes it's 1.2, 1.5, 1.8. Sometimes it can be 10. Sometimes it could even become 100. All right. There is no limit to the factor of safety. There is no technical limit to the factor of safety. Okay. Factors of safety are usually given as industry standards. So depending on the application and depending on the materials that you're using, you might have a prescribed factor of safety. So say you are using very predictable materials and you are putting them into a function where the forces are relatively known, like you know pretty much what the types of forces that you'll be dealing with. Then you might use a lower factor of safety. But then as soon as you start putting people's lives in the balance, your factor of safety goes up. So in the case of bridges, you might have a factor of safety of 2 or 3. In case of airplanes, maybe a factor of safety of 10. But bear in mind, when you might ask the question, why not just make everything to a factor of safety of 100 and make sure it's 100% safe? And that's where we come back to here, safety versus cost. Because in order to make something safe, it usually means you have to either add more material or make it out of a more expensive material, a stronger material. And those are generally more expensive. Okay, so while there is no technical limit to the factor of safety that we should have, there is always that fine balance between, am I just over-engineering this? Or does it actually need this factor of safety? Do I actually need to make it bigger than it needs to be? Where do I draw the line? And that is what the factor of safety is basically. It's where you draw the line. Okay, cool. So yes, are there any particular places in the assignment where you have issues? Maybe I can focus on those. Web analysis. Okay, sure. Just briefly, so the order in which we do our analysis is dependent on our load path. So we have part A and part B here. Part A is rotating, is having some power and is rotating at some torque. And we're trying to transmit that exact power and torque to shaft B. And in order to do that, we have our coupling, all right? So the forces transfer from our shaft, from the center of our shaft, go out to the key, through the hub, through the flange, through the bolt, and then out the other side to the center of the shaft B. So that's why we do our analysis in that order. We start from shaft, key, hub, flange, bolt, out. And each one of the designs of each of those components then affects the subsequent component. So depending on the length of our key, it will affect the thickness of our hub. Then the thickness of our hub will influence the thickness of our flange. Thickness of our flange will then influence the positioning of our bolts and the number of bolts we use, and so on and so forth. So first one obviously is the torque analysis, finding the torque based on the power that we're given. Next one is the key, where we have to find our key length. Hub analysis to find our hub thickness and then our hub diameter. And then we come to the web analysis. Right, so the web analysis is purely dependent on your hub analysis. So depending on your hub outer diameter that you determine in the hub analysis, you can then calculate your web thickness. And that's what you're trying to find, the thickness of this red region here. All right. So can anybody tell me what type of forces will we be experiencing on the web? It's always useful to first define what type of forces you'll be working with. So this hub is turning with some kind of torque, and it's creating what kind of force on this red surface? If you look at it, the force would be acting like this. And you can see that it's on the surface and not perpendicular or not shooting out of the surface. So it's a shear force. So if we're looking at shear force, we'll be also looking at shear stress. So that's the first important thing that you have to identify. And shear stress is equal to, not shear, the shear stress on the web will be equal to the shear force divided by the area of the web. The area of the web is this red region. Okay. To find our force at each stage, we have to relate it to the torque. So once we've calculated our torque from our torque analysis, we can find our force. Force times distance. If we make force the subject of the formula, that becomes torque divided by the distance. And the distance is taken from the center of the shaft to where the surface is, or the center of the surface. And if you look at that, that distance would be the radius of your hub. Do you see that? From the center of your shaft to the top of this surface is nothing but your radius of your hub. So depending on your hub diameter that you found in the previous analysis, hub analysis, you can then solve for your shear force. Right. Taking that bit of information, you can plug it into the formula. So shear stress of the web will be equal to whatever shear force you have from here, divided by the area. Now the area is the area of the red region, area of your web. This area is your circumference of the hub. So this is a circle originally, and we are going to try and imagine cut the ends and then stretch it out, and it becomes just a long piece. And we're going to try and turn that into a rectangle where this distance, the length, is the circumference of the circle, so pi d, and the thickness or the width is your flange thickness or web thickness. That's the area of our stressed surface. So area of the web is width, web width, web thickness, multiplied by pi times hub diameter. Okay, and our shear strength or shear stress is just the shear strength of the material that we're using. So the flange or the web is made out of cast iron. If we go back to our assignment, the shear strength of cast iron is given to us, 5 megapascals. So can we use the circle area formula? So pi r squared. No, because we're not trying to find the shear surface isn't the area of the hub, if you get what I mean. We're not interested in this. We're interested in the outside surface only, not the face surface. If we were interested in this surface as the the stress surface, then yes, we'd use pi r squared. But as it is, we're interested in the circumference. So pi r or pi d or 2 pi r. All right. Cool. I hope that answers your question about the web analysis. Any other questions from any of the other analysis that we have? Just bear in mind that 15 marks comes from your calculation report and 10 marks comes from your drawings. And your drawings, you have to produce a 1-dimension drawing showing all the dimensions that you've figured out through your analysis, and 1 drawing showing the assembly of the parts. So 1 assembly drawing and then a dimension drawing of your choosing. You could either do a orthographic projection or an isometric view with dimensions, whichever one you find easier. Any other questions or areas you're not quite sure about? Have you all actually started the assignment yet? Okay, haven't started. Well, that's okay. You still got a few more weeks. It's during week 14. So just make sure you don't leave it for the last minute because you also have your project to be working on, your presentation and all that. Can I discuss the bolt analysis? Okay, sure, Kristen. I'll go to bolt analysis now. So this session will actually end in 8 minutes, but I'll start a new session where I'll discuss the bolt analysis right now. So just use the same login information that you used to get into this session in the next one that I'll open up. All right, just use the same meeting ID and password to join the second half of this tutorial. And at the end of that session, I'll be taking attendance. So please make sure you attend the second part.